Awesome. Thank you so much for joining us today here at the episode 4 of our season 5 now lecture series. Welcome. This is the lecture series that we've been putting on as sponsored by the Network for Ocean Worlds Research Coordination Network. My name is Shannon McKenzie. I'm one of the co-leads. We have several other of our co-leads here on the call, Chris German, Allison Murray, and our esteemed project manager, Catherine Pietro. And today we are excited to invite two fantastic speakers to talk to us about exploring the ocean world Europa and our own ocean world here, the Earth. And we're hoping that by having these two perspectives put together, we can stimulate some interesting discussion of how exploration of these two worlds is sometimes parallel, and what we might learn from each other. So to kick us off, we're going to start with Diana Blaney. She'll give about a 20-minute talk. We'll have a little bit of time for questions after her talk, and then we'll switch over to Joseph Cook, who will give, again, a 20-minute talk, a few questions just for Joseph, and then we'll kind of open it up, and hopefully by that time you've thought of a really meaty, juicy question that'll get us all thinking about Europa and the Earth as tantalizing ocean worlds. Okay, so to introduce Dr. Blaney, Dr. Diana Blaney is the principal investigator of the Mapping Imaging Spectrometer for Europa, also known as MISE, which is on NASA's Europa Clipper mission. She and a science team member of the multiple Mars rover missions. Her research is focused on the analysis, data collection, and development of spectrometers to determine the surface composition and chemistry of planetary bodies using short wavelength infrared reflectance spectroscopy, thermal emission spectroscopy, and laser-induced breakdown spectroscopy. And today she's going to give us a tutorial all about MISE. So take it away, Diana.
So let's get this. Okay, can you see my slides?
Yep, they look good. Thank you.
Okay. All right. So I'm going to talk about MISE, and I'm going to spend a few minutes talking about Europa, although I expect this crowd kind of knows why Europa is so exciting. And then I'm going to talk a little bit specifically about how MISE is approaching some of these problems, and then get into some of the gory technical details of the instrument. Please feel free to send me questions or ask questions. And we've got a nice kind of review article where a lot of these images came in Space Science Review. And if you haven't seen that special issue, there's everything you could want to know about Europa Clipper in very, very gory detail there. And I think it's going to be a useful resource for the future. So Europa is one of the ocean worlds in our solar system. Its ocean is maintained through something called tidal heating. Basically, the other Galilean satellites are in orbital resonance and pull up a tidal bulge on the surface of Europa, that the relative distance of the planets causes that bulge and the planet to noticeably enlarge and contract. On Io, which has the most tidal heating, it's kind of called a runaway volcanic world. On Europa, it's produced this nice, stable environment, which has many of the ingredients for life: lots of water, essential elements from both the formation of Europa and from impacts, chemical energy, both from tidal heating and perhaps from geothermal, and stability. We think the system has been there for a long, long time. And so that makes it a really exciting place to look for a habitable world. Clipper 101, we actually launched on October 14th. We just flew by Mars in early May. We're on our way back to get another gravity assist from Earth in December of 2026. And then we get to Jupiter out in 2030. Once we get to Jupiter, we will do a bunch of phasing orbits and then start a series of 42 flybys, kind of starting in the 2032 time period. So Europa Clipper has a very long horizon. We started working on the instruments and proposals in 2015, and we'll get our first really core science data back in about in 2032. Um, that has us basically flying close to Europa and in and out. This is because of Europa's very heavy radiation environment. Spacecraft, their electronics can't survive in orbit around Europa for very long. And so it's easier to go in close, then come back out. It's a very rich and complex payload. There's gravity and radio science to get the interiors. There's a radar, sounding radar. There's a plasma instrument called PIMS. There's a magnetometer to measure the induction from Jupiter's radiation belt. And then in the optical instrument, there's MISE, which is an imaging spectrometer from 0.8 to 5 microns, a UV spectrometer, a couple cameras called ICE, wide angle and narrow angle, and a thermal emission imager. So the overall goal of the Europa Clipper is to investigate its habitability. And notice we're not directly looking for life, but we're basically trying to find out if it's capable of supporting life. Um, and we're doing that by studying Europa as an integrated system. We're studying the interior structure, understanding how deep the ocean is, where the crust is, and the energy transport through it, the geology, how the materials um, are move and shape, the tectonic. You'll notice that Europa has a lot of tectonic fractures and stuff. What drives them? What's the time scale? How does the body evolve? How and what are the geologic processes that could link the ocean at depth to the surface? MISE is kind of focused on the compositional thing. Basically, what is Europa made out of, and what does that tell us about habitability? And then we also have a thing to look for current activity. Are there currently active vents, geysers, things like that going on where we might be able to directly sample the ocean and perhaps um, have more direct measurements of habitability and what's going on in the ocean. Um, MISE is made by a team. This is the MISE team at the launch. We are a group of scientists from many different institutions. The hardware was principally built by JPL and APL. The dancing penguins is our team logo when people do things well. And then that's a picture of MISE in the clean room before we put the blankets on. Um, and it's a pretty big. So the science for MISE was kind of focused on the proposition that Europa is complicated, and the story of its surface composition is also very complicated. There is a lot of processes which could be moving material between the surface and the subsurface. In addition, once it gets to the surface, it has a very variable radiation exposure that varies by location and age on the surface. And these actually produce very distinct compounds in the surface, which could be used to age date the surface. Um, there's impact processes, there's meteorite processes, there's basically a lot of different things that can confuse each other. For instance, one of the big things that people have been arguing about are some of these asymmetric water bands and whether they're caused by hydrated sulfates or uh, um, acid products or other things. Um, a lot of the evidence for the sodium chloride is coming from radiation damage, colored centers. So there's just a lot of different processes, and what you're seeing on this at the surface may not be fully representative of what's going on. So we kind of decided to focus on using an imaging spectrometer so that we actually tie composition and geology together. Um, and so we can basically then provide specific provenance of materials to their location. So one of the ways that we're kind of doing that, a good example is organics. There are a lot of organics that are in the outer solar system that are not related to Europa's uh, ocean. And there could be compounds that are formed by radiolytic properties. However, if you look and you see even a highly degraded organic, because it's been exposed um, to Europa's radiation environment, that is lying with like a geologic feature, like a band or stuff, that gives you evidence that the source material is perhaps into the interior of Europa. So basically, looking for evidence of organics, even if they've been heavily processed by the radiation environment, and understanding their spatial ties to the geologic processes, um, understanding the salt chemistry, and then also water ice has a lot of interesting process products up here. Its phase, its structure can tell you about temperature, age, and understanding the ice. And then if you got something really going on active, you might actually be able to see a thermal emission signature. Imaging spectroscopy is a kind of a tried and true technique in the planetary surface. It has sensitivity to a broad number of compounds over a wide range. And this area in here, the 2.5 to 3 micron range, where Europa is very, very dark, but there's wasn't really good Galileo data. However, there's a lot of strong organic features at 3.4 microns. You can tell the difference between some of the sulfates and the hydrosulfuric acid, and really a lot of other things. And so this wavelength range is kind of the new area that we're going to be kind of focusing on for MISE. We're focused because we're a flyby mission. The data comes in, the spatial resolution is a factor of how close we fly to the planet. So when we're flying down at, say, 100 kilometers, we'll get 25 meters per pixel, but at higher elevations, it'll be much lower. And we've kind of broken those down into three regimes: local, regional, and global. Local studies very specific small scale global processes and looks for isolated outcrops of material. Regional studies things like a regional scale geologic feature like a chaos and stuff. And then you need the global coverage to understand the radiation processes and how those impact the surface composition. I'm not going to spend a lot of time here. These are the key instrument parameters, but it's a very high throughput, fast instrument using a single focal plane array. Um, this is kind of MISE on the spacecraft. We're about a meter by uh, cubed, and this is kind of how we are on the spacecraft. Way down here. The red is our remove before flight cover, which makes it easier to spot us in the spacecraft pictures on the ground, but they took it off here. And you can kind of get a feel for how big this spacecraft is by this image of Europa Clipper against a basketball court. So MISE has a pretty complicated design that was driven in a large part by the radiation environment. We are, even though we're in the outer solar system, we use a cryocooler to get the spectrometer and temperature and detector down to cryogenic temperatures. That's because the way the solar panels and the nadir viewing deck of the spacecraft are oriented, we don't have a good view to space to be cooled radiatively. This radiator that we have here, it actually is to dump heat from the cryocooler that is cooling it and not directly cooling the interest. We've got a three-axis telescope, a scan mirror, which allows us to do two things. One, at a distance from Europa, we can scan back and forth and cover the whole planet and large areas for our global. At the closest approach, we can use that to do image motions compensation to get sufficient integration time to build up good signal to noise observations. And so all of our observations are planned based on the spacecraft speed. And unlike, if I don't know if people work with EMIT or some of the large terrestrial imaging spectrometer data sets, we get 12 observations per flyby. So our data volume is relatively modest compared to what people who are working with terrestrial imaging spectroscopy in Greenland and some of the icy areas are. So we have to spend a lot of time actually planning specifically where we're going to hit. Um, the optics, again, it's a three-axis telescope. So here's the scan mirror. Light comes into the telescope. Oops. Yeah, light comes into the telescope, off the scan mirror, into the spectrometer. And the spectrometer itself is about the size of a Coke can. So it's a what's called a Dyson, using a calcium fluoride prism and slit, so the light comes through the slit, goes through the prism, um, is then reflected off a gold-coated custom diffraction grating, back through it onto the detector. The detector has an order sorter filter that that divides the light, keeps the light from different orders from contaminating them. So we have and there's small gaps at where the seams, but we've got a filter that goes from 800 to 1450, 1450 to 2600. And then at the longer wavelengths, we have a linear variable filter to minimize background contamination. I mentioned the radiation environment being a chemical signature, but it was also one of the main drivers for the MISE instrument to derive. We had to basically encase the entire optical part of the instrument in tantalum. It's got 9 millimeters of tantalum. If you had 1 millimeter of aluminum, you would get equivalent of 40 milliradians of radiation exposure. With the tantalum that we have, we got it down to 20 kilораds. The detectors see more than that in your Earth orbit. So what was driving that shielding was the secondary electron. So basically, every time we slowed one of these high energy electrons, it would cause a cascade of secondary electrons. So what we ended up doing is using the scan mirror to oversample. And so basically we are taking between 10 and 20 observations for a single pixel, and then doing onboard radiation processing. That our integration time thus is set not by the how bright or how much signal we can get, but how long we can tolerate before we get 10% of our pixels having radiation noise. So this has led to some more complicated things like onboard processing to remove the noise, and keep our data volume manageable. We have to have our own memory because we have to store all this, and because the processing, the data collection happens much more faster than the processing. And because we're doing the scanning based on the position of the spacecraft, every time there's a maneuver, we have to update all of our observations. And we kind of figure this out by taking MISE type detectors to a synchrotron thing and doing a lot of testing before we started building the instrument. Um, Thermal control, we're a cryogenic instrument. So basically we've got to have the spectrometer and the focal plane really, really cold, and be integrated to a 0 to 50 degree spacecraft. So the thermal isolation and the thermal design was also very challenging for MISE. Um, this is our nominal flyby again with the global. The joint scan is when we're taking data at the same time as UVS and eThemis. This is to get the global scale. Then as we get closer, we go into the regional scale, which is about 300 meters per pixel or less. And then when we go into the local scale, it's like 50. And the closest approach for Europa Clipper is 25 kilometers. And so we'll get about 7.5 meters per pixel there. This is kind of what we expect our data set to look like, where we take all of the spaghetti things from the second slide and combine that with our required lighting. We can't take data when it's dark. So we'll get pretty good global coverage. Here we're getting about 82.3% at 10 kilometers or less, and a lot of it is in the 5 kilometers or less globally for maps. And basically these will provide three-dimensional data sets for locations and then what their spectral reflectance in the 800 to 5,000 micron. For the regionals, where we get a couple of those a flyby, so they're going to be at very specific locations. And then finally, for the locals, they're just going to be little postage stamps here and there, to get a picture of Europa. And the regional and local, we're taking data all the time that we have good lighting. So there's just not a lot more we can do on the higher resolution. So that's kind of the high order picture of what MISE is going to do at Europa and kind of what's motivating us to go there. So any questions?
Thanks, Diana. That was great. Chris German has already pre-populated the chat with a question. So Chris, if you want to unmute and start us off while other folks are thinking about their questions.
Yeah, thank you, Diana. That was wonderful. A real case of popping the hood and showing us what's inside, what MISE is made of. So I know.
Sorry, Diana, just to let you know, your email is showing in the share.
Stop sharing.
Don't overshare. Nicely done, Shannon.
Yeah.
So Diana, I know MISE is going to be far superior to anything that was on the Galileo mission, but in terms of this issue of radiation and how that affects composition, is there going to be an opportunity to do any kind of like for like comparisons of like flying over the same places and seeing how the composition might have evolved from?
Oh yeah, definitely. I think that's one of the things that we're really going to be focusing on. We used a lot of the Galileo data as our base map. A lot of it's
Mhm.
that, and there are hints that things are different, and there's also some evidence that some processes may be going on, and like think about if there was an eruption or a geyser that might not have any of the radiation signature, or the ice may be
Right,
finer grained and stuff. So there's going to be a lot of that change detection. And because the Galileo's data was generally at the kilometers per pixel kind of, and higher
hmm,
scale. Some of the better spectra are like 25, 26. Our global data sets will allow us to do really good
okay,
comparisons.
right. That's where the global
Yeah,
perspective comes in.
yeah. But
Great,
we've not really seen Europa at these higher resolutions, and
right,
the experience from both Earth and Mars is that your compositional diversity really starts increasing as soon as you start doing imaging spectroscopy at the scale of the geologic features you're studying.
right. That makes sense. Yeah. Thank you.
All right, I'm going to use host's prerogative to ask the next question. What compound are you most looking forward to searching for with MISE? Like, what are you
I
hoping to see in the spectrum?
I am hoping to see a CH stress someplace. I think because of the radiation environment, things may get highly degraded, but I'm really hoping to see something in the 3.4 micron region. I think that's an area where uh, we don't have really high resolution stuff. I think it's going to be isolated, and I think that I'm not optimistic we'll be able to do a lot of the detailed chemistry that perhaps mass spec and stuff do, but I really do think if we can pinpoint locations where there's evidence of oceanic organics, I think that would be a really exciting measurement. And a lot of
Yeah,
people are starting to do laboratory work to support really what do organics look like in this environment.
awesome. All right, Aaron, I see your hand up, but feel free to drop your question in the chat to make sure we get to it later, or write it down for yourself, because we are going to transition to Joseph's talk, and then open it back up to broader questions. So let's thank Diana again while Joseph is pulling up his slides. So Joseph Cook has worked on various topics relating to glacier albedo modeling and monitoring since his PhD from 2008 to 2012. He has held a range of academic positions across geoscience and computer science. He currently holds a fractional position at Aarhus University and spends the majority of his time as head of R&D at the Green Software Foundation, where he works on developing standards and tooling for sustainable computing. Today, we've asked him here to talk about multispectral imaging and spectroscopy and how that bridges the microscopic to ice sheet scales of investigating our own ice and the biological and physical processes there. So take it away, Joseph.
All right. Thank you. Thank you very much. Really excited to be here. Thank you. Today, I'm gonna be telling you about efforts to map life on Earth's ice today, focusing on one particular area, hoping that that's somehow instructive for elsewhere. But before we get into the modern stuff, I would like to just very quickly take a trip back in history to 1870. And the explorer that you can see on the screen, Adolf Nordenskjold, it just made landfall on the western coast of Greenland and started an attempt to cross the ice sheet. And on the way, he made extensive and very colorful notes in his diary that make a fantastic read. But I'm going to pick out a couple of pertinent observations that he made to set the scene. And the first one is that he noticed a dark discoloration to the ice, not in patches, but as a kind of continuous veil over the ice surface, which he speculated was cosmic dust originating in space. And he was concerned about the albedo effect of this cosmic dust, wherein the darker the ice, the more effectively it absorbs solar energy and it melts faster. And he even suggested in his diary that this space dust could be, quote, the greatest enemy of the massive ice due to the melt accelerating effect. And Nordenskjöld also complained a lot in his diary about the difficulty that he had just walking around and finding solid ice to sleep on during his crossing, because of the high frequency of these bucket-like holes in the ice surface with this black sediment on the floors, which he named cryoconite, for meaning cold dust. And while he was out there, he examined this sediment and discovered that it was bound together by biological material, including filamentous algae. And there are so many of these that he frequently tripped into them and moaned about getting wet feet, wet boots. And he also got a sodden sleeping bag. So what he wrote in his diaries, he complained about having a sodden sleeping bag because he couldn't find spaces between these holes large enough to lay himself down to sleep. So 120 years passed by, and only a few papers mention cryoconite again, or dark ice on Greenland again, until we get into the satellite remote sensing era. And also this also combined with a new urgency to understand sea level rise. And this sparked new interest, because now we can see from space what Nordenskjöld could only see with his eyes while he was traveling around on foot. And now suddenly we can see that Nordenskjöld's dark ice, those areas weren't just isolated local phenomenon, but actually he was looking at a keyhole view of something covering tens of thousands of square kilometers on the fastest melting areas of the ice sheet, where the ice sheet's contribution to sea level rise originates from. So in the past decade in particular, there's been a lot of interest in mapping this dark stripe and working out what its intraannual variability is and what's its likelihood to expand into the future. And to know that, we have to know what processes are causing the discoloration and what's their relative importance.
Joseph, I'm so sorry to interrupt. I'm still seeing, oh, okay. You just switched slides for the first time? Okay,
yes.
Just making sure. That looks great.
Yes, fast forward to the modern day. The first post Nordenskjöld hypothesis about the darkening of the ice sheet focuses on dust, harking back to Nordenskjöld, but this time not cosmic dust, but dust that was once deposited high on the ice sheet during the Holocene, got incorporated into the ice, and then advected towards the margin, where it's now being exposed and expressed onto the surface as the ice ablates as a light absorbing particle. And this hypothesis is supported by what you can see on the screen, this very geological looking wavy pattern that you can observe in the satellite imagery. But then a little later, people also realized that there was a biological component to the dark ice in the form of algal bloom that forms directly on the ice surface. And field studies have revealed this algae to be among the darkest particles on the ice surface, because it produces this photoprotective pigment that it uses to protect itself from being sunburned, from being fried by the irradiance in the summer. And this pigment happens to be a dark brownish color that ends up being the emergent color of the ice surface, because this algae is basically omnipresent to varying concentrations across the ice. So a series of field studies, including some that I was involved with, used field spectrometry and lab experiments to show that in localized patches where the concentration of these algae is very high, they can reduce the albedo. Excuse me. They can reduce the albedo relative to clean ice by up to 20%. And those same studies actually found that the mineral dust component on the surface was very, very weakly absorbing, which was somewhat surprising, but it's now been replicated over and over. And the minerality of the dusts found on the surface in the dark zone are nearly all just very weakly absorbing quartz and feldspar minerals, and they have a negligible effect, a direct impact anyway, on the ice albedo. So on the back of those findings, there was this relatively intense period of trying to map those algae from UAVs and from satellites. And you can see some albedo and surface classification maps that were derived from multispectral UAV imagery from a paper by Ted Stone et al. On the right-hand side of the screen right now. These are from Upernavik in northwest Sweden. And then the first attempts to map the glacier algae from satellites, they typically used either used RGB imagery, or they used just very simple detection algorithms such as the famous red edge, or the NDVI, normalized difference vegetation index. And there are also experiments that used the measurement of the chlorophyll absorption feature at 680 nanometers, because those algorithms have been proven to work very well for other algae, like red snow algae in the mountains and other photosynthesizers in other environments. And on the left-hand side of the screen right now, you can see the key figure from a paper by Wang et al. They applied the red edge, which is a band ratio, to estimate the algal concentrations across the dark zone. And there have been other efforts too, usually using band ratios or some other sort of statistical-based models, typically using a small spectral library of field data. But those methods kind of suffered a bit in the context of glacier algae, because the chlorophyll signature for the glacier algae is often much more subtle and ambiguous than it is for the other species, because it's masked by this photoprotective pigment, and the absorption of those photoprotective pigments overlaps with the chlorophyll, making quantification from band ratios or from measuring the chlorophyll absorption feature quite uncertain. And also at the time, there was very, very little ground data to give us a lot of confidence in the retrievals. I also did a study that mapped an area in the southwest part of the Greenland ice sheet, using a decision tree model that learned a set of field spectra reduced down to Sentinel-2 resolution, and used that to map the algae. And that's what's on the right-hand side of the screen right now. It's not fully quantifying the algal concentration in terms of cell counts, cell concentrations, but just categorizing the ice into low, medium, and high concentration classes. But again, basing algorithms like that on field spectra is imperfect, mainly because there's a limit on how many field spectra can practically be collected. So the spectral library is typically smaller than one might ideally like for training an algorithm like that. And it's also, with the field spectra, it's hard to isolate what specific processes are contributing. You have mixed signals in the field measurement. There's a lack of pure end-member spectra to interpret. So to a large extent, the satellite mapping done up to that point was, we might think of it as quite top-down. We had medium confidence that we were really mapping what we thought we were, because the algorithms were fairly crude. They had limited ground data to act as a source of truth. The physical configuration of the ice itself was not being explicitly accounted for. You might argue that there was an overemphasis on the region around Kangerlussuaq in the southwest, because that's where logistics for fieldwork were most convenient, and it became a very popular place to go. So to progress from that point, I felt very strongly that we needed a new strategy that was less about starting with the remote data and trying to mine insights from it, and instead being something more physical and bottom up, that attempted to meet the satellite data already having empirical information about the signatures that we might expect to find. And radius of transfer modeling was our entry point there. And when we started down that road, we didn't have field measurements or samples available that we could use to get empirical optical properties for the glacier algae or for the mineral dusts. But we did have information about the pigmentation of the cells, and we knew the size and shape and the local mineralogy and the particle size distributions, etc. So we set about generating synthetic optical property data from that information, and optical property data sets that already existed in the literature. And we created a database of optical properties for algal cells and for some mineral dusts, and we packaged all that up into a Python translation of Mark Flanner's SNCR model and called it BioSNCR. And that was a big help because it allowed us to explore hypothetical scenarios and create synthetic ground truth data, experiment with indirect albedo reducing effects and all that kind of stuff. But we were also still stuck with hypothetical optical properties for the most important impurities that we wanted to explore. So fast forward again to this ERC project, Deep Purple, beginning. And this gave us some more opportunities to go back into the field. And at that point, I thought it was critical that we gathered empirical optical properties for the glacier algae and for the mineral dusts, because that's what would give us confidence in our ability to model the surface and then make use of synthetic ground truth data and train models for interpreting multispectral data and run experiments, and ultimately to separate out signals from different darkening processes. So I had two PhD students who would work on this problem. The very first thing that PhD student Lou Chevrolier did was to measure the optical properties of the glacier algae directly. And she transported them back from the field, and living samples were placed into cuvettes inside an integrating sphere. And we directly measured the optical properties and pushed them directly into BioSNCR. And what you're looking at on the left-hand side of the screen right now is those are the empirically measured absorption cross-sections for actually snow algae as well as the glacier ice algae. And we also did this for mineral dust, and we did it for samples for a range of sites around the ice sheet. And at the same time, we also put a lot of work into upgrading the original BioSNCR model so that we could use the most up-to-date rigid transfer solvers, included liquid water and other light-absorbing impurities, including cryoconite granules, lots of accessibility improvements. There's a no-code web app and all kinds of stuff. And we tested the model by recreating the conditions found in the field and recreating field spectra. And as you can see, there's three examples on the screen right now. We were basically able to reproduce near perfectly the field spectra using realistic config. So at that point, we turned our attention back to remote sensing again, making use of this new empirically informed modeling capability, and generated large spectral libraries covering many permutations of the ice physical properties, illumination conditions, concentrations of the different impurities. And that's what gave us what we needed to start running the BioSNCR model in inverse mode, where instead of giving the model a set of config and generating a spectrum, we gave it spectra and it generates the config. And this is a way that allowed us to algorithmically interpret multispectral data over the dark zone. And what we found was that the spectra generated by the inverse modeling was always extremely closely matched to the field spectra, and the retrieved config was realistic. So then we set about to apply the model in inverse mode to multispectral satellite data. And what that means is that we can go pixel by pixel through a satellite image and invert the spectra to yield estimates of the ice physical configuration, the impurity concentrations in each pixel, and that yields maps with layers for each parameter. And we've also trained a neural network to do this, to do the forward and inverse modeling for us, so that now you don't necessarily have to use what's a relatively slow Python model with a very large multi-gigabyte database of optical properties that comes along with it. Instead, you can just use a very lightweight, portable, language-agnostic neural network model instead, with basically indistinguishable accuracy across at least the most useful subset of BioSNCR's parameter space. And what we were most interested to retrieve from satellite data using the inverse model was actually the darkening effect associated with each parameter, so that we could get a sense of what actually explains the color of Greenland's dark stripe. So for each pixel, we run our inversion model to get the most likely configuration of the surface based on the spectral signatures. And then we pass that config back to Biosnicker in forward mode, and then systematically generate new spectra where we reset each parameter to a clean ice reference value. And that process yields an albedo delta for each parameter that we can map and compare and rank. And what you're looking at now on the screen is the result of that process. There's albedo deltas, or darkening effect, for each parameter for some example pixels in a Sentinel-2 image for a region in the southwest Greenland ice sheet. The maps are albedo delta maps. The spectra show the inverse model predicted spectrum for the marked pixels, with the albedo from each of the Sentinel-2 bands superimposed on as black dots. So what might we have learned from doing this? Well, while all the work was happening to constrain the optical properties and the impacts of glacier algae and mineral dust and map them and what have you between 2010 and 2020-ish, poor old cryoconite got forgotten again, which feels a bit crazy to me because it's one of the most strikingly obvious albedo reducers on the ice. It's jet black, and it's so frequent that poor old Northern Skjold couldn't keep his feet out of it. Well, we brought it back in Biosnicker and into the mapping studies, and as a result, we think that cryoconite could be actually the primary driver of the low albedo of Greenland's dark stripe, followed by the glacier algae and the physical development of the surface crust, liquid water, mineral dust, etc., all playing secondary roles. And interestingly, these models also suggest that the albedo reducing effect of the algae and the mineral dust is quite consistent with what was published before using other methods too. But it was exceeded by the effect of the cryoconite, which has mostly been omitted from previous studies. And what's satisfying about this is it actually kind of feels like we've finally converged on an explanation for the dark stripe that where what we see from the multispectral data is actually consistent with what our eyes tell us on the ground. And in the last, I think I've got 1 minute left, but I'm going to use it to just stray a little bit further into speculation. But I think this hierarchy of processes, with cryoconite being the main driver and algae in the physical configuration next, I think this makes a lot of sense because it brings together a lot of loose ends from what were previously quite disparate arguments about the drivers of darkening. And we have the downwasting, releasing mineral fragments from the ancient ice, which in turn stimulates the algal growth and the formation of cryoconite granules, because both of those need the mineral fragments as a substrate and as a source of nutrients. So while the minerals aren't directly reducing the albedo, really, they are stimulating the growth of algae and formation of cryoconite, which means they've got a very critical indirect effect. And that is consistent with that very geological pattern that we showed earlier in the satellite imagery from earlier. So what does it mean for the future? That I don't know. But my personal hunch is that it might imply the potential for dark zone expansion for a while, until maybe we hit a physical limit imposed by the high elevation extreme of where the Holocene dusts are exposed on the surface. So maybe there's a possible glaciological control on the dark stripe, but I don't actually have hard evidence for that. I'm kind of throwing out a hypothesis, and that's all I got. Thank you very much for listening.
Thanks, Joseph. Let's thank our speaker. We'll have a couple minutes for questions just for Joseph, and then we'll open it back up. A question from Mike Molaska in the chat. I think he's asking, have you ever used your spectral retrieval algorithm to look at other planets?
No, no, I never have. And honestly, I never even thought of it, but it's a great idea. I'd love to.
Yeah, he's got more details in the chat, but that was also something that struck me as very similar to what we try to do at the Galilean satellites or elsewhere. We have very limited, good optical constants, and churning those through some black box model to see what we can pull out is a difficulty we share.
Yeah. Yeah.
I also had a question. I love that you started with the history here. Was there ever a period where the presence of algae was like not commonly accepted or controversial? Was there like some data that really, closed the book on that?
Yeah, I would say that there was a period like that. I think it depends. It depends. There's kind of sub-communities within sub-communities here that have different perspectives on it. And as you saw in the talk, it was known that there was a biological component to the ice way back in the 1800s. But I would say that the consensus was definitely that there were abiotic processes, and the ice was close to inert for the majority of the previous century. And I'd say there were some papers that got published in the 1980s, some American papers and some Japanese papers in the 1980s and 1990s that started to hint at a growing adoption of the biological role. And then it was really in the 2000s, really in the 2010s that it got widespread recognition, and there was a proper literature started to get built.
Based on the spectra, the IR spectra, is IR?
Well, yes, and also a kind of flurry of field expeditions to Greenland that did a lot of microscopy, brought home samples, culturing experiments, etc. And just, at that point, it's kind of uncontroversial that there's a large biological component to the ice, and then also the spectroscopic measurements showed that translates into an albedo reducing effect.
Cool. I think there's a great astrobiology parallel there, so thanks. All right, let's open it up. Chris, you want to go next, and then we'll go to Aaron.
Yeah, mine was another question for Joseph. So the cryoconite holes form because the initial things that land are dark. As they burn their way down and make the holes, presumably they have the potential to undergo sort of chemical reaction and change color. Would you see that in the spectra, or is it by that point it's actually the depth of the hole that gives the darkness? So it's a property of the light, so you wouldn't be able to see that.
Yeah, I think I see what you're getting at. The cryoconite forms on the surface. It doesn't land as cryoconite. It's
right.
It's an aggregate of mineral dust that gets bound up in biological material on the ice surface, and as the granule forms, it becomes dense enough to settle rather than just being washed away in the meltwater. So you get collections on the surface, and when you get a collection, when you get a patch, it absorbs the solar radiation, effectively warms up, and kind of drills its way down into the ice just because it's hot on the ice. And then it reaches some kind of thermal equilibrium where the melt rate at the bottom of the hole is equal to the melt rate at the surface, and that determines the hole depth. So as you get changing illumination conditions, changing air temperature, etc., the depth of the hole reacts to that. And so it's not black material that lands and then forms a hole. It's kind of like it's more sort of integrated process. We haven't noticed any changing color when the material gets to the bottom of the hole. It's different. It's a different color when it dries out. It's kind of like palish brown when it's dry, and then gets dark when it's wet and it's in the hole.
I was thinking of it more from the perspective of it's non-water ice, or it's non-water material that's interacting with water, and there must be at least some melting somewhere happening there. So there's that potential for chemical reaction. I was just wondering if that was a spectrally resolvable thing, or whether it's just, I mean, is the darkness of the cryoconite just because of the shape, so the light doesn't come back out?
It's the dark, this dark humic material. It's all bound up in this very dark humic material. Yeah.
Okay, the material's just one color.
The material's just dark. Yeah.
Thanks. Aaron, go ahead. You're still muted, Aaron, if you're trying to speak. Maybe you can drop it in the chat and I will attempt to ask a question in the meantime. So this is for both Diana and Joseph. I think one of the parallels that I saw between your talks was having to balance the unknown, you know, in situ data with these beautiful like remote sensing measurements that you took. I wonder if you can speak to some of the ways that you see the interplay between in situ or lab-based measurements and how those feed into remote sensing and some vice versa.
So I'm highly dependent on laboratory measurements, and I think that the just the environmental conditions, you're talking something that's 100 and 125 K, the phases of ice and stuff are just not the same. But I do think that field work, in situ experience with glacial and terrestrial landforms opens people's minds to the types of process and like what insulation driven landform might look like. And I think the issues of surface texture, grain size, those kinds of things, our appreciation, I think, is emerging from terrestrial experience and their experience with optical constants, and then starting to apply that for planetary surfaces. We're highly dependent on our optical constants and trying to figure things out. And having something that works on Earth gives us good confidence that at least it's a valid approach to start with.
Yeah, similar answer from me. I think if we had not had field observations and physical samples to take home and analyze in a lab, we probably would have mistaken the spectral signature for being one from reddish colored dusts, and just assumed that that explained the spectral signatures that we saw in the dark zone and thought no more of it. It's really only by going and looking under a microscope and seeing these algal cells that we realized there was more going on.
Well, that's a great set of answers, motivating more lab and field work for all of us. So thank you very much. Thank you all for tuning in, and let's all thank our speakers again. That was a fantastic pair of talks. This is the last so far episode of this season. I have secret plans of maybe convincing others to maybe keep going. I've announced it now, so maybe I can twist some arms. So to our now members, stay tuned for the steering committee meeting next week, May 28th. Thank you all for tuning in, and have a great rest of your Wednesday.
Yeah, thanks, Diana and Joseph, for joining us.